So just like the Cartesian coordinate system, we also have to consider vector derivatives in a spherical coordinate system. So our vector derivatives, to recap, are the gradient, we have the divergence, the curl, and the Laplacian. And what we must do is consider these for a spherical coordinate system. And above shows the various equations that must be implemented. So what we're going to do is an example using the theorem for divergence, or Green's theorem or Gauss's theorem, which is also known as. I'm going to check the divergence theorem for the above effective function. And we're going to use as our volume this hemispherical bowl of radius r, which is situated in the xy plane and centered at the origin. So here is our theorem for divergence theorem. And what we have is the integral of the divergence over a volume is equal to the total flux, or the total amount of fluid which is passing through a surface per unit time. That's given as the integral of the v dot dA, where dA is an infinitesimal surface element. So the first thing we do is we're going to use this expression here in order to determine our divergence of the vector function v. So divergence of v is equal to, I'm just going to plug the values in here first. So let's get 1 over r squared, take the derivative with respect to r of r squared, and this is the VR component, so it's r cos theta, plus 1 over r sine theta. We're taking the derivative now with respect to theta of sine theta multiplied by our v theta component, which is the r sine theta, plus 1 over r sine theta and the derivative with respect to phi of our v phi component, which is r sine theta cos phi. Okay, so let's work through this. So now when we break it down, what we're going to get is we have a r cubed cos theta. So the derivative of that is going to give us 3r squared. The r squares will cancel, so we're left with 3 cos theta plus we have the derivative of r sine squared theta. Over here, I've given what the derivative of sine squared theta is going to be equal to. So it's equal to 2 sine theta cos theta. So we have 2r sine theta cos theta all over r sine theta plus, well, the r sine theta is going to cancel in our final term. These are going to cancel. So we've got the derivative with respect to phi of cos phi, which is going to give us minus sine phi. Okay, so that's the first step. So let's just do it a little bit neater here. Our r sine theta is going to go, so we're left with 2 cos theta. So finally what we have is 5 cos theta minus sine phi. Okay, so that's our first step to solving this problem. Now the next step is we must integrate it over our volume. Now our volume is d tau, and d tau, as we saw in the previous lesson, d tau for the spherical coordinate system is equal to r squared sine theta dr d theta d phi. Okay, so let's work out the integral of this. Okay, so what we're working out here now is the volume integral, the divergence of v d tau, which is going to be, so we've got a triple integral here. We've got respect to r, theta and phi. We just worked out the divergence of phi, which was 5 cos theta minus sine phi. Here we have r squared sine theta dr d theta d phi. So now what are limits for our integrals? Well, for r it's between 0 and big R, okay, which is the radius. For theta, it's pi over 2 because you're only considering a hemisphere. So here we go from 0 to pi over 2. Okay, so that's for our polar angle theta. And for our azimuthal angle, we have it from 0 to 2 pi. Okay, so now let's just work this out. So if we integrate with respect to r, we have r squared, so we get r cubed over 3. Okay, and I'm going to put in for the big R, so we've got r cubed over 3. Then I'm going to do the integral with respect to phi, so I'm going to leave the theta alone for the moment. And if we do the integral with respect to phi, we're going to obtain 5 phi cos theta minus cos phi, that was between 0 and 2 pi, sine theta d theta. Okay, so what we have here now is this for phi is going to work out as 10 pi cos theta. Okay, so I'm going to bring the 10 pi aside, so we have 10 pi r cubed over 3. And we're left with our integral between 0 and pi over 2 of sine theta cos theta d theta. Now, when you work out the integral between 0 and pi over 2 of sine theta cos theta, what we're going to get is a half. Okay, so this is given in here. Okay, so our final answer then is, since this integral here is equal to a half, our answer is going to be pi r cubed, 5 pi r cubed over 3. Okay, so this is the integral of our divergence effective function v over some volume.